Hi, good day everyone. In this video, we'll be talking about the action membrane potential. In the previous video, we talked about the graded membrane potential, and we mentioned how we can attain the graded membrane potential by what? By the stimulation of the axon hillock. And we mentioned that the graded membrane potential, the purpose of the graded membrane potential is to allow is to move the cell from resting membrane potential to threshold voltage. And we mentioned that threshold voltage is about minus 55 millivolts. So we are moving the cell from minus 70 to minus 55 millivolts. How are we going to do that? We say it's the concept of summation by the releasing of excitatory neurotransmitter EPSP. Excitatory postsynaptic potential is minus 55 millivolts, and we say that this excitatory neurotransmitter EPSP can be attained by two means. The first one is the what is by temporal summation, and the second one is by spatial summation. We mentioned that temporal summation is when one presynaptic neuron is stimulating the postsynaptic neuron, and spatial summation is when we have more than one presynaptic neuron stimulating one postsynaptic neuron. So every stimulation is going to be what will be summed and will be given out as what as the neuro stuff. Now let's now talk about action membrane potential. Once the threshold voltage has been reached, what is going to happen is that the sodium ion channel on the axon is going to be opened. Are you getting me now? Sodium ion channel on the this thing on the axon is going to be opened. Remember that I mentioned something like this. We have a neuron, we have the axon, and we have the axon terminal. So what you are seeing here, this place is the cell body. This place that you are seeing is the cell body. You understand? This place is the axon, and this place is the axon terminal. You understand? That place is the axon terminal. So hope you understand now. So don't be confused. It's just the way I do it. It's quite I don't know how to go. So let us proceed to what you're saying. Now, sodium ion channel is going to be opened immediately that we move from minus 70 to minus 55. We move from minus 70 to minus 55. The sodium ion channel here is going to open. I get me now. It's going to open the sodium ion channel. And once it opens the sodium ion channel, what it's going to do is that, remember that in the first video that I made, I said sodium is more outside than inside, right? Sodium, there are more sodium outside than inside. I get me now. So what is going to happen is that once the sodium ion channel has been opened, more sodium will flow inside of the cell. I get me now. More sodium what? Will rush into the cell. So sodium, let us say sodium, there are more sodium outside of the cell than inside of the cell. So more sodium what? They will rush inside of the cell. They will rush into the cell to move from minus 55 to about plus 33 millivolts. I get me now. Now, what is going to happen is that not all sodium ion channel is going to open at once. No, they can't open at once. All of them can't open at once. They will be opened periodically. So once this one opens, sodium ion flows inside to attain plus 33 millivolts, which means making the side inside of the cell to be what? It's minus 30 millivolts. Sorry, I said minus 30 millivolts. To make the inside of the cell to be super positive. You understand? Hyper positive. Are you getting me now? Now, the inside of the cell is very, very positive now. Once this channel has allowed the passage or influx of sodium ion to the extent that it has reached plus 30 millivolts, it is going to close. The next sodium ion channel is going to open, making more sodium to what? To flow inside. To the extent that this part will be what? Will be plus 30 millivolts. I get me now. Once it attains plus 30 millivolts, this one will be close. Then the next one will open to allow the influx of sodium ion to the extent that it becomes what? Plus 30 millivolts. Then this one too will close. Then this one too. So it goes like that periodically till it reaches the what? Till it reaches the axon terminal. I get me now. Till it reaches the what? The axon terminal. Now, once it reaches the axon terminal, it is now another case. Remember that sodium ion is flowing inside. As sodium ion is flowing inside of the cell is becoming more positive, very, very positive, hyper positive. You understand? And this hyper positivity makes the impulse to flow So as this one is become plus 30 plus 30 plus 30, impulse is flowing through what? It is flowing through the axon to the axon terminal. I get me now. Now, once it reaches the axon terminal, you see this channel that is here? This channel here, can you see? That I mark in pink here. It is calcium ion channel. You understand? It allows the influx of calcium. Remember that calcium is also a what? Calcium is also a positive charge. It is a what? It is a cation. You understand? It's a cation. So it allows the influx of calcium ion, which means in this case, it is calcium ion that will be what? That will be flowing inside, not sodium, not potassium. So calcium ion what? Calcium ion will flow inside of the cell in this place. Ca2 plus. What I want to write is this Ca2 plus. You understand? Calcium ion what? Will flow through the what? Through the gated channel into the what? Into the cell. To the extent that it becomes plus 30 millivolt as well. This place becomes plus 30 millivolts. Now, what is the purpose of calcium ion? You see this stuff here? This stuff that I mark in blue here, the one that I marked in blue here, they are known as stamina bulb. They are known as stamina vesicle. You understand? Let me write it somewhere. We have we will call it what? We will call it stamina vesicle. Terminal vesicle is like this. It's like a button. You understand? And inside of the terminal vesicle, we have what? We have some stuff. We have some chemical inside. What do we call those chemicals? We call them neurotransmitter. That is where we got the neurotransmitter I was talking about the other time. You understand? We call them neurotransmitter. So the neurotransmitter can be inhibitory, can be excitatory. You understand? So as the impulse is flowing through the distance, is flowing through. Once calcium ion, once calcium ion what do I want to say? Once calcium ion flows influx of calcium ion into the what? Into the cell membrane, what's going to happen is that it's going to allow the shrinking. It allows the shrinkage of the what? Of the terminal vesicle. Just like it's as if you press a balloon, you understand? As if you press a balloon. To the extent that what? It releases its what? It releases its content. It releases out neurotransmitter. Now, this is what is going to happen. This terminal vesicle here is going to bind with the what? With the button that is there. It's going to bind. So the terminal vesicle, let us say we have another one here, is going to bind. And once it binds, what it's going to do is what? It's going to release, it is called exocytosis. It's called exocytosis. So it's going to what? It's going to release its content. I get me now. It's going to release its content, the neurotransmitter. Where is it releasing it to? That's the question. Where is it releasing it to? It will release it outside. You understand? Outside of the space. Can you see? There is a space here. It is releasing outside of the space. And what is this space called? It is called synapse. Which means after this, let us say this is the neuron that we are dealing with now. It is now releasing neurotransmitter to the what? To another neuron. You understand? Which means this neurotransmitter can be inhibitory and it can be excitatory. Which means this neurotransmitter that is being released, it is going to allow the next neuron that is at resting membrane potential, if it is inhibitory, it is going to allow it to reach what? Threshold voltage. And this one too, once it gets here, it's going to release another neurotransmitter to allow another neuron as well. So that is how it goes. That is how information flows through the neuron. You understand? So action potential is attained when the influx of sodium ion makes the inside of the cell to be hyper positive, and once it's hyper positive, information flows through the what? Through the axon till it reaches the axon terminal. Once it reaches the axon terminal, the calcium ion channel at the axon terminal opens, allows the influx of calcium ion. Once it allows the influx of calcium ion, it is going to allow the terminal vesicle to bind with the terminal bulb. Once it binds with it, it's going to compress it to the extent that what? It is going to release its content. Where is it releasing its content to? It will release the content outside of the cell. And that outside of the cell is a space. The space is called what? It's called synapse. And synapse is the space between the presynaptic neuron and the postsynaptic neuron that allows the what? The flow of that allows the flow of what? Of signals. You understand? So that is how it is being attained. Now, there is now a problem. What is the problem? The problem now is that inside of the cell is now positive and neurotransmitter has been released. Let us take for an example. You went for a race. Are you getting me now? You went for a race. You were racing. Going, You are going, you understand? You are going, till you reach the what? The finish line. So this is the finish line. Once you reach the finish line, what are you going to do? You won't be you will rest. You understand? You won't continue running. Are you getting me now? Except there's something else happening. So you won't continue running. What you are going to do is you are at action potential before. You are at action. What you are going back to is what? Is resting. You must go back to rest. Because you have done what you are supposed to do. You have reached the finish line. So what you are just going to do is what? Go back to rest. Are you getting me now? Now, how do a cell go back to resting membrane potential? Which means, how can a cell move from plus 30 millivolts to minus 70 millivolts? That is where the problem is now. How are you going to do that? This is what is going to happen. Now, you know that I mentioned in the first video that inside of the cell has more potassium ion. Are you getting me now? It has what? More potassium ion than sodium ion. Are you getting me now? Now, what is now going to happen is that what? As potassium ion has flow inside, to the extent that the inside of the cell is becoming positive. You know this part that I mark white now. Look at it. It is now potassium ion channel. It is potassium ion channel. Once it sees that the inside of the cell is very, very positive, it is very, very positive, and it wants to take it back to negative, it is going to open. Once it opens, potassium ion will flow outside. Potassium ion will flow outside of the cell. Potassium ion flowing outside of the cell. Potassium ion flowing outside of the cell. Are you getting me now? Potassium ion flowing outside of the cell. So they keep flowing outside of the cell. You know, the more the potassium ion that flow outside of the cell, the more negative the inside of the cell becomes. Why? Because inside of the cell we have anions that is binding with what? Potassium. Those anions are unable to go outside of the cell. So as potassium is going outside, you understand? As potassium is going outside, we're having anions, and this anion is unable to go outside, which means the anion will make the inside of the cell to be what? To be positive, to be negative rather, to be negative. Now, there is now a problem. Remember that the cell is more permeable to potassium than sodium, which means as it is flowing out, once it flows out to an extent, this gate closed. But this gate, remember the name that I called it? I called it leaky potassium ion channel. Which means it can leak. It can allow what? It can allow leakage. You understand? As it is trying to close, we have reached minus 70 millivolts. I get me now. We have reached minus 70 millivolts. What is it going to do? It will try to close. As it is trying to close, some of the potassium will leak outside. So excess potassium is going out. They will be going out. They will be going outside. I get me now. So we are going to have about minus 90 millivolts. And we want to reach minus 70 millivolts. That's where the problem is now. Now, what I'm explaining now is that potassium is flowing outside till it reaches minus 70 millivolts. It is now trying to close to the extent that what? It is trying to close. It is now overflowing to the extent that we have minus. Now, it's just like this. Look at it. This is a tap. We have a tap here. We have a bucket. You understand? Are you getting me now? Now, this is where we are supposed to fill our buckets. Now, this is a tap. Let me illustrate it again. Let me clean and illustrate. So we have a tap. We have a tap. And we have the switch. Now look at it. This is where we want the water to reach. This particular place. This is where we want the water to reach. Now, remember that we have allowed this is minus 70 millivolts. You get me now? Minus 70 millivolts. So as we reaches this place, we try to what? We try to close the tap. But there is no how. There will still be some droplets that will drop from the what? From the tap as we are closing it. Hence, it is going to go beyond what we are supposed to have, and that is minus 90 millivolts. Now, since we have minus 90 instead of minus 70, what are we going to do? We are going to remove some content of the cell. Are you getting me now? We are going to remove some content from the bucket water so that we what? So that it will allow the cell to be what? To be back to normal resting membrane potential. Now, what is going to happen is this. That is where, remember I said we have three, this thing. We have three. We have the sodium potassium ATPases. Sodium potassium ATPases. we have the leaky sodium channel ion, the potassium channel, and the sodium channel. Now, what is going to happen is that this is what is going to happen. I drew potassium ion channel and stuff like that the other time. Now, this is what I want. Leaky potassium. So this is sodium potassium ATPases. This one on the sodium potassium ATPases. I get it now. Sodium potassium ATPases. And the reason why they call it ATPases is because it uses energy. Now, let me draw it back here. So let me say this is the sodium potassium ATPases. What does it allow? This is what it does. You know the inside of the cell is minus 90 millivolts now. Minus 90 millivolts. So what we want to do is we want to make this inside of the cell to be what? To be around minus 70 millivolts. So what you're just going to do is what? What you're just going to do is, what is the main problem before? The main problem is that excess potassium flows outside of the cell. I get me now. Excess potassium flows outside of the cell. I get me now. So those potassium that flows outside of the cell, we try to bring them back into the cell. So about 2 potassium will flow back into the cell. But as 2 potassium is flowing back into the cell, 3 sodium is flowing outside of the cell. Now look at it. We want to make inside of the cell to be positive. We are removing 3 positive and adding 2 positive. Is that logical? No, it is not logical. Now, how is it going to help? Yes, it is going to help. Why? Because what causes the hyperpolarization, what causes the minus 90 millivolts is the excess leakage of sodium and potassium ion, not sodium ion. So taking out sodium ion out inside of the cell is not going to change the what? It's not going to change the concentration gradient. You understand? What we just need there is the what? Is that we must return the potassium ion into the cell. As we return the potassium ion into the cell, what happens to the cell? The inside of the cell becomes positive to about what? Minus 70 millivolts. Once minus 70 millivolts has been attained, then we can now go back to resting membrane potential. And the next postsynaptic neuron is going to take over what you have been explaining since morning. Now, this is the diagram. This is the graph. I have a graph here. Now look at this. This is the graph. So this is minus 70 millivolts. This is what I was explaining. Field initiation, that's summation. Till it reaches what? Till it reaches threshold. Once it reaches threshold, it's moved from what? It's moved from minus 55 to about plus 30. It is plus 30, not 40, sorry. It is plus 30. Now, once it goes like that, once action potential has been this thing, then it comes back. It's supposed to stop at minus 70. But because of leaky potassium ion, what it's going to do is what? It is going beyond it. You understand? Now we are trying to go back to resting membrane potential. That is when potassium ion will now flow inside and sodium ion will flow outside. So this process of moving from minus 70 to plus 30 is termed depolarization. The process of moving from plus 30 to minus 90 is termed to minus 70 is termed repolarization. And the process of moving from minus 70 to minus 90 is termed hyperpolarization. You understand? You don't see this period. This period that it is trying to move from minus 90 to minus 70, from minus 70 to minus 90 to minus 70, it is known as refractory period. This is the period whereby the cell cannot transmit any impulse. I get me now. It cannot transmit any impulse because it is trying to go to what? It is trying to go to resting membrane potential. I get me now. It is trying to go back to resting membrane potential. So it cannot transmit any impulse again. So that's well known as what? This place is well known as refractory period. And we have type of refractory period. We have the relative refractory period and the absolute refractory period. So I'm going to explain that one later. But for now, just know that this place is the relative refractory period, when the cell is not transmitting any impulse. You understand? Because it is trying to go what? It is trying to go back to resting membrane potential. So that one is clear like that. So this is what I was trying. This is stuff. This is summation. Look at this. This summation. It is not sum. It is not summing. It comes back. It comes back till it reaches what? Till it reaches the threshold voltage. Once it reaches the threshold voltage, it goes to what? Plus 30. Can you see that it is 30? It is 30 here, not 40. So it goes to what? It goes to this thing. And look at it. Look at what they say here. EPSP. Can you see? And IPSP what? It pulls it down. EPSP takes it up. You understand? So look at it. Once this is depolarization, this is repolarization, this is hyperpolarization, this is refractory period. You understand? So that is what we have here. So this one is showing the terminal vesicle. Look at it. This terminal vesicle, what I drew the other time. So look at it. We are releasing neurotransmitter to the what? To the outside of the cell, to the next distance, synaptic cleft. So that is what you have there. So that is how action potential is being initiated, and it is therefore transmitted into the what? Into the postsynaptic neuron. So look at it, the postsynaptic neuron, and the same thing that happened in the presynaptic neuron happens in the what? In the postsynaptic neuron. I hope you understand the concept of resting membrane, action membrane, and the gradient membrane potential now. And in the next video, we continue on neural signaling. Thank you so much for listening, and subscribe for more.